This presentation is about SUWMBA, the Site-Scale Urban Water Mass Balance Assessment tool developed by the CRC Water Sensitive Cities. This module gives an overview of the tool. It runs through its scope and functions. It talks about the principle of mass balance, which it is based on, runs through some of the key inputs and outputs and layout. For those who really want the detail, there's a SUWMBA user manual. And this module includes an introduction to the tool, the structure of SUWMBA, instructions for using it. On the CRC website, there are multiple case study applications of the tool and other related reports. SUWMBA assesses the performance of an area that we call an urban entity. This is the combined effect of buildings, pipe systems, and water technologies, together with soil and vegetation. SUWMBA can be used for urban units up to 4 hectares or larger, up to 50 hectares if no rainwater harvesting system exists. Larger areas can be analysed with SUWMBA if the urban entity is divided into smaller, uniform units. It's intended for guidance and overall screening of different development options, for example by architects, engineers, local authorities, as a step towards detailed design or engineering. SUWMBA can't replace professional judgment or detailed modelling. SUWMBA is based on a core principle of urban water mass balance of this thing we call the urban water entity. This enables quantified urban water performance indicators which all interrelate because they're relating to a predefined volume of urban space. It calculates water flows as annual volumes using daily time-step data. You can see from the equation below that it looks at all inputs: precipitation, centralised water flows, decentralised water flows, recycling internally, and all outputs: evapotranspiration, stormwater runoff, wastewater flows, inflow to groundwater, and reuse, and uses that to compare the change in storage within that urban water entity. SUWMBA integrates 4 submodels. These are hydrological models, a water demand model, a water harvesting model, and a storage model, together with piping configurations. It uses a consistent set of nomenclature across roofs, pavements, other impervious surfaces, irrigated surfaces, non-irrigated surfaces, and other pervious surfaces, such as permeable pavement. The water demand is broken down by irrigation, toilet and washing machines, dishwashers, showers, tap and bath water use. Because it's using a mass balance, all performance indicators interrelate. So many are possible. Some of the core indicators that we'll describe include those around resource efficiency. We can look at the overall water efficiency, looking at total residential use of environmental water per person, or internally sourced water, to get a measure of water supply internalisation. It also lets us look at hydrological performance, which is the ratio between the post-urbanised hydrological flows or fluxes relative to the pre-urbanised flows. Indicators are calculated from that water mass balance for any three-dimensional defined system or entity. SUWMBA quantifies how flows are affected by both urban design, such as the perviousness of land cover, and it also considers water servicing options such as rainwater, stormwater, and recycled water. This allows screening of various water-sensitive interventions. It provides a comprehensive picture of water performance by capturing the interactions between the natural and built environment with regard to water flows, together with socio-technological systems such as water technologies. This gives greater clarity of the impacts of architectural design, water-sensitive technology, and environmental conditions such as rainfall, climate, or soil conditions. Inputs to this tool include site information, for example, the population and number of dwellings. So for example, in this red bounded area, inputs would be the number of people, we've got roof areas, etc. The environmental context, for example, the location and time frame. The location is important because it can then use the correct rainfall lookup library from the Bureau of Meteorology. zones within the area. It is broken down by land cover and their characteristics. For example, pervious green space of different types of vegetation, areas of driveways, etc. The fourth input is usage of alternative water sources such as rainwater harvesting, purple pipe recycling, etc. It also considers water demand and supply characteristics, as well as hydrological model settings. The layout, the main sheets are the start sheet, input site sheet, where the data related to the site being analysed is included, and then the results sheet. There are also a range of hidden sheets, such as index of input parameters and detailed results for advanced applications. The input sheet lets users add details of the entity, site information, the area, the popular, the number of dwellings. The environmental context includes the soil type and potential evapotranspiration, also from Bureau of Meteorology lookup libraries. A critical area is the zones within the site. So the areas must total up, but the areas of different roof, road, paved, grass and tree lets users add detailed characteristics of those areas, and whether those surfaces are connected to water harvesting or not. It lets you include usages of alternative water sources, for example, rainwater and stormwater or grey water, and also water demand characteristics of the site, such as outdoor and indoor use. Part 5 looks at water use and water demand characteristics, and Part 6 is the hydrological model component, which looks at soil moisture, the field capacity, which lets the model determine the demand or lack of demand for irrigation of water. Outputs include the water mass balance. So it includes quantification of all inflows, so total megalitres per year of rainfall, also characterised as millimetres per year, imported water into the system, water sourced from within the system, so that's internally harvest water from recycling or stormwater or rainwater capture, and wastewater sourced from the study area or leaving the study area as a sum of total inflows. It also looks at total outflows, including evapotranspiration from the various surfaces, the stormwater discharge, stormwater recharge to shallow groundwater, and infiltration also to groundwater, to total outflows. It then conducts a water mass balance, ensuring that total outflows equal total inflows, less change in storage. SUWMBA calculates 25 different indicators, the site's built area fraction, the vegetated area fraction, fractions of permeable and hard surfaces. We call these midpoint indicators, but also, so they're more indicators of design of the site to give architects, etc., an understanding of how their design is then impacting the endpoint indicators. For example, the fraction of rainfall that is converting to stormwater discharge, or the naturalness, how close to pre-developed is the stormwater discharge, the number of stormwater discharge events, the fraction of rainfall that infiltrates, etc. Endpoint indicators give a quantification of the hydrological performance of the site. This can be used to compare, for example, existing, business as usual, and water-sensitive design. So in this picture, we're showing the natural flows of water as and inflows as blue, precipitation, evapotranspiration, and there's a range of outflows, including stormwater runoff and wastewater discharge, with bigger arrows representing bigger flows. SUWMBA lets you put numbers on all of those flows. The results, and SUWMBA has been designed to connect with the Infill Development Evaluation Framework, also developed in IRP4. That lets us quantify, using these pentagram diagrams and multi-dimensional diagrams, the water performance, so the stormwater discharge component and the water efficiency component, and a range of other hydrological performance indicators that can then be added to assessment of outdoor, private space, dwelling amenity and function, and urban heat, so that we can compare just how significantly development of business as usual is improving or creating negative impacts in the dimensions of water, heat, and amenity. Other indicators can also be analysed in more complex hydrology. So for example, the water supply self-sufficiency, the number of people supplied based on imported versus internally supplied water, the fraction of area with deep root zone, or really any of the 25 performance indicators of SUWMBA. SUWMBA was developed in the CRC Water Sensitive Cities. The tool and the manual are available on the CRC website from the link shown here. The tool is really developed for desktop computers and laptops using a Microsoft operating system. It's based in Microsoft Excel and can be learned with relatively little training. For comments or questions, please email the CRC at info.crc.watersensitivecities.org.au. And if you're really interested, there's a range of publications. A detailed description of the methods incorporated in the tool can be found in the research article Moravec et al. 2020, and that also compares what the functionalities of SUWMBA can do to about 25 other different hydrological models. Its great strength is in site-based characteristics, water-sensitive interventions, and quantified performance indicators of the site. A case study with the tool is presented in an article by Renouf et al. 2019. Further documentation about the concept of water mass balance and quantification of urban water performance indicators can be available from the following articles. Understanding urban water performance at the city scale using water metabolism. Understanding urban water performance at the city scale using water metabolism. And a research article by Tariq Fahey. Points of this presentation: SUWMBA calculates water mass balance at site scale, both natural and anthropogenic or human influence flows. It examines the influence of both the built form design and water servicing features.